folks, let's go ahead and get started. So let's talk about. So let's go ahead and get started so we can get through. We got a lot of different activities we want to have you all do today. So let's talk about. Let's have a little discussion before we get into the round robin of this this first activity that you did. So you have these Superballs that you bounced. So what have we done? Let's go through some of these questions. We've done that. We've done these simple questions already, but let's go through them because it's important. The more we talk about this and use the language, the easier it's going to be for you to talk to your students about it. So when the ball's in your hand before you drop it, does it possess energy?
Yes.
Yeah. All right. What kind of energy does it possess?
Gravitational.
Yeah. You know, potential energy is fine. Gravitational potential energy is even better. And that's the most important. You know, we can talk about a whole bunch of different types of energy, but that one's the most important because that's the one that's going to take part in this activity. What kind of energy does the ball have just before hitting the floor?
Elastic potential. Not yet.
Just before hitting the floor.
Just kidding.
No, that's going to help out a lot in a minute. But that's a good question. So does it have elastic potential energy right before it hits the floor?
No. Not before it hits.
Okay, why not?
Yeah.
Of course, I got rid of the blue pen.
Over there.
Thank you. All right, so we have potential energy up here right before we hit the ground. What kind of energy do we have?
Gravitational potential.
Right here. Oh, I see what you're saying. Since we're not really touching the ground yet, we still have a little potential energy. Okay, that's fine. I like that. And then it's mostly what? Right, it's moving, right? Okay. All right, so now this is important. This is the most complex part. I say here as the ball bounces, it contacts the floor for a very short time. Do you buy that?
Yeah.
I mean, it's not. It's not instantaneous, though, right? I mean, is there a certain amount of time that it's in contact with the floor?
Yeah, because it has to take the time to hit the floor and smush back up. That's very scientific.
Technical term is
So I like this. The smush
factor.
The smush factor. Exactly. All right, so here we are. This point right here. So this is point A. This is what I mean by diagram. You can do it any way you want. So there's point A, point B, point C. So this point C where you've got the squish factor happening. There's a point at which it comes to, it's going down and stops and comes back up, right? Okay, so let's talk about that point right in between. What's happening there? What forms of energy do we have there?
Elastic.
There is going to be kinetic energy all through this process except for one instant, right, when we turn around. At that instant, let's talk about that instant in time. That instant in time, the energy is in what form? Potential energy. What kind of potential energy? Okay, so let's think about this. This is really interesting, right? That energy, here's what's cool about this, right? Is you have all this potential energy up here. You've got all this potential energy. You've got converted. You've paid that out of the bank. You've got all this kinetic energy, active energy. And then it gets converted back into potential energy. Different type, though, right? We have gravitational potential energy, kinetic energy. Point C, we have what kind of? But what kind of potential energy? Elastic potential energy. And now what's going to happen? That elastic potential energy, where is it going to go?
It's compressed and then it will release.
I like the word release. It's going to be released into what form of energy?
Kinetic.
Wonderful. Point D, we're moving back up, right? That elastic potential energy got converted, as you've described, back into kinetic energy. Beautiful. Do we get it all back?
No.
Does it come? How high does it come?
About 80% of its original height.
All right, let's hear. I want to hear the data. What's the data? How high do we get? You all have a percentage? Like how high do we get? 14 inches from the original, right? Oh, you washed 14 inches? No, not the plate. You mean you washed 14 inches? Which one? What you guys do now? So it went from 60 inches to 46 inches. So what did you all get?
Ours actually about 49.
Okay. What did you all get? 52 inches out of 60? From 5 feet? Right, you guys have it. This is the one I'm taking. That's a good point. Where did you all do your? Right here. Where did you all do yours? Interesting. Interesting. It'd be interesting to go through and see if our data is consistent. So it may be that on the sort of rougher surface here. Well, let's talk about this. Why don't we get it all back? Some of it is lost as friction. I like that answer, but let's talk about precisely what that means. Friction where? So you're talking about between the surface and the ball, the friction between the surface and the ball. What do y'all think?
I think the ball is moving whatever surface it hits, ever so slightly. Some surfaces can take it up energy.
If it was only the surface, and it wasn't this, why would you have any difference between this and the Play-Doh? No, I'm defending your perspective. If it was only friction, if it was only surface interactions, then Play-Doh and Superballs would do the same thing. But there's something going on. What did you say? Say what you said again.
I said that the ball is absorbing some of the energy when it hits the cement, kind of like almost like a shock.
So you're saying inside the ball. What form of energy is being converted into that? Well, there is elastic energy. So there's a bunch of things happening in this ball. One is this elastic squeezing that you're going to get a lot back. But there's also something else happening. It's not important to be elastic. Heat. Yeah, there's going to be a little bit of heat. There's going to be a little bit of energy that goes to the heating of this ball. Okay. Now that, again, the heat sounds a little weird because you don't think of this thing. But you've probably experienced, if you play racquetball or you start really knocking objects hard, they get hot, right? Okay. All right, let's talk about the Play-Doh now. Oh, did anybody try second and third heights? Second and third bounces? What's the same? Okay. So you're saying, it's a little complicated. What do you mean by it's the same? So you're losing the same fraction of energy each time? Is that what you mean?
No. Okay, so it bounced, and then it got to 46 inches, but then on the second, it like reduced by half, but then the third is about the same. So then it dropped again to 4.
Oh, really? So you're saying your second and third bounce are about the same? So that so how many times have you guys just do it at once? Really? And you got consistently the second and third bounce was the same? In the end, this is complicated how the energy is going to be lost each time. My hypothesis would be that you lose the same percentage each time, but that may not be the case. We can talk about it. Let's get on to So what that would mean is that the elasticity of the ball is determining how high the second, third, and fourth bounce are. Properties of the ball. So let's talk about the Play-Doh. So what happens with the Play-Doh? You drop the Play-Doh, what happens? I like this though. This is an interesting point. So what did you just say there? Okay. So well, let's talk about the physics of that comment. What's the difference between the two? In light of that comment, what was a key difference between the two the balls, Play-Doh ball and this ball.
Sound that makes.
How much does this make much sound when you drop it? I mean, I didn't really have you observe that, but I guarantee you that Play-Doh makes a lot more noise than this thing. Because it's wasting energy, it's losing energy, right? So let's talk about why does that Play-Doh ball not bounce back up? Well, no, it bounced a little. No, it didn't. You know, it depends on what kind of material you have. Some materials you could drop it and you wouldn't bounce at all, right? The Play-Doh bounced a little bit. Okay, so where's the energy go? This is a crucial question. So this is the important part. The difference between these two processes. Where did that energy go? Into the what? Part of it went into sound.
Oh, sorry. Which transferred to a
Okay, this is really a great observation. So say that again out loud.
So
Or you already said it out loud. The shape change.
You know, but the rubber ball, the Superball, was able to change shape and then bounce back to its original, where the Play-Doh didn't do that. It changed shape, it stayed that shape.
This is a really important point. There a bunch of energy went into deforming. In both cases, the balls get their shape changed when they hit the ground. They get deformed. All right. In one case, you get that energy back. In the other case, you don't get that energy back that you put in.
Because I guess how I'm thinking of it, it's like a situation one is controlled and one is not controlled. Because I think of the ball, the rubber ball, the fact of being more controlled, like you say, you get it back. But this one is, it kind of releases, goes all over the place, so it's not as controlled.
I see what you mean by control. Like the energy isn't organized. It's not
Contained.
Yeah, it's not controlled or captured. I mean, one way of thinking about this, when you get into understanding the difference between a rubber ball and clay, like what's going on the molecular level, it has to do with the way atoms and molecules push past each other, whether they do it in a way where they slide a bunch, where they're never going to get back to their original position, or whether they just stretch a little bit and then they come back.
And it seems to me, too, a difference might be with the Play-Doh, that if I dropped it off of a 6-story building, it might not bounce at all, because all of the energy goes into deforming it to a point that it's not able to bounce back up at all, which is different from the Superball.
Right.
We tried
The height,
to
the higher we went, the more height bounce we got, but I was thinking there gets to be a point like this where that's not true.
We changed the shape of them. We tried a teeny Play-Doh ball, and it bounced like 3 inches. So we also talked about, the mass, the size of that ball.
Yeah.
Because I think that it absorbs more of the shock the bigger it is.
Right.
The shock of the bounce. When it's smaller, it bounces back.
That's interesting. So you made a more elastic. Maybe there's a surface to volume issue there. You got more sort of surface tension or something happening. I like that. Okay, great. I mean, the other thing to think about, heat is not. So one of the questions, do you think heat plays a part here? Do you think that which ball do you think would heat up at the collision? I don't know if I really put my money one way or the other, but I want to talk about it. I mean, sometimes there aren't easy answers to these questions. Which one do you think heats up more?